Good morning. We begin lecture 17. As I mentioned, today is the day we discuss about the spectral analysis, and this I believe will be a very useful tool and lots of interesting principles that we can build upon. So, a quick summary of what we have discussed in the last class, and then we dive into today's lecture. We are looking at filter banks, where we have we use the alphabet M to denote the number of channels. So, always keep that is a very common term, we call it as an M channel, and of course there are special cases where M equal to 2, M equal to 3, and of course larger numbers like M equal to 16 and 256 also. So, M is characterizes a family of filter banks, the most general form, and we are looking at uniform filter banks that are obtained through the shift of the frequency or the magnitude response. So, in the last lecture we defined H naught of Z, H1 of Z as H naught of ZW. So, H naught of ZW, if you look at it in the on the unit circle, it will be H1 E of j omega. W is given by e power minus j 2 pi over m. This is W subscript m. In case I forget to write down the subscript, the default is m. So, if you write it in terms of the argument, it will be e power j omega minus 2 pi over m, which basically says that the frequency response of H naught gets shifted to a center 2 pi over m, and of course H2 will be shifted to 4 pi over m and all the way to m minus 1. And we showed that if we were to apply the polyphase decomposition, then we got a form of this type. I hope you are able to get it to this and this part is comfortable. Then we looked at the properties of the DFT matrix. In general, we talk about an endpoint DFT, endpoint DFT or IDFT, and that is why we have chosen M there and N here. If you are talking about M channel filter banks, then the DFT size will also be N equal to M. So, endpoint DFT or IDFT, that is what we have generally talked about, and you find that the structure of the DFT matrix, which you would have studied in DSP, we made the following observations, again probably a repetition for most people, that the W matrix, which represents the DFT, is unitary. And if you take W dagger W, you get n times I, that is the definition of a unitary matrix, and which also tells us that the inverse can be very easily obtained for a DFT matrix. It is just the conjugate transpose with the scale factor. The dagger symbol is a matrix operation, transpose followed by conjugation. In the case of the DFT matrix, it is symmetric, so therefore transposition gives you the same matrix back, so it is effectively just conjugation of the matrix. So, that is sort of the very easy form that we have to have. There is a what we refer to as a normalized form of the DFT matrix. So, in the normalized form, again this is more of an observation. So, in the normalized form, so that the forward and the inverse transform look similar, we define the forward transformation matrix as 1 over root n times the W. Okay. So, basically there is a scale factor of 1 over root n that is given to normalize the matrix. So, in that case W prime inverse will be 1 by root n W dagger. So, basically you have a 1 over root n scale factor for both matrices and not just 1 over n for the inverse, and this is sometimes used, but very often in signal processing when you look at it primarily as a transformation and you want to have very similar looking transforms and you want to have a normalized transformation, then you would take this form. But in DSP our basic definition is W as given in this slide, and W inverse will have the 1 over n scale factor to get the appropriate identity matrix. Now, the decomposition that or the task that we were asked to do is to look at this type of structure and look at what happens when you replace this with the DFT matrix, not the conjugate transpose of the DFT matrix. So, I hope you had a chance to look at it. If not, we will just spend a few minutes so that you get a chance to sort of visualize what it is, because that is an important element in the discussion that we are going to be having today. So, H naught of Z, again going back to the polyphase decomposition, H naught of Z, write it down in the polyphase form, L equal to 0 to m minus 1, Z power minus L E naught of Z power m. So, an important point that we want to make is previously we got the shifted versions by the following form. In the previous case it was obtained by H naught of ZW. So, if I want to get the transpose conjugate, let me look at ZW inverse. So, I just want to look at what does HZW inverse actually, what does it represent. So, if I were to look at H naught at ZW inverse, you can see that this actually corresponds to writing it as H naught of e power j omega plus 2 pi over m, correct? Absolutely correct, E L Z power m. Okay. H naught, if I were to substitute H of ZW inverse, this is what I would get. Now, also look at what you get for H of m minus 1 as per the original definition. Okay. All these are as per the original definition. This would be H naught of ZW m minus 1, that would be H naught of e power j omega minus 2 pi over m into m minus 1, okay, close bracket, close bracket. Okay. Look at the argument of the exponent e power j omega minus 2 pi over m into m minus 1. If you simplify, you will verify, you can verify that this is nothing but e power j omega plus 2 pi over m. Okay. So, basically H of m minus 1 and this H naught of Z W inverse. So, if you were to follow the same notation that or the convention that we were using, if H1 is equal to H1 H naught of ZW, okay. So, basically the power of W becomes your subscript for the filter, then this would correspond to H of minus 1, which would be this would be H naught of ZW inverse, this is nothing but H of m minus 1 of Z as per the original representation. Okay. So, basically if you were to write down in the following manner, H1 minus 1 of Z, which is actually equal to H of m minus 1 of Z. If you were to write down the expression for this, this would be equal to summation L is equal to 0 to m minus 1. Again substitute and verify that what you get is W raised to the power L and within bracket Z power minus L E L Z power m. Okay. One more, let us take the general case. If you were to write down for H of minus k, okay. So, H of minus 1 is H of m minus 1, this will correspond to H of m minus k, this is equal to summation L equal to 0 to m minus 1 W k L within bracket the same expression Z power minus L E L Z power m. So, if you go back and look at the figure that we had previously obtained, now basically what we have is that this matrix is no longer the W dagger, it is actually the W matrix. If you go back and look at our expressions, you notice that these are all the coefficients of the DFT matrix. Did I get that correct? Yes. If you had negative powers, then it will be part of the IDFT matrix. Yes, this is correct. Okay, so these are all coefficients that you would find in the DFT matrix. So, that is why we now have the DFT matrix here, and very quickly let us write down the transfer functions. Okay. So, between this point and this point, the transfer function is h naught of z, if you go back and look at the expressions there. Okay. Now, between this and this point, second branch, that will come out to be h of minus 1 of z because of the DFT matrix. The polyphase components are the same, the delay chain remains the same, and we know that h of minus 1 is nothing but h of m minus 1 of z, and go on all the way to the last one. The last transfer function between the input and the last transfer function, that comes out to be h of minus m minus 1 of z, and that will come out to be h1 of z. So, the summary of the observation is that you could very well have done it with the DFT matrix as well, if you wanted to do it. There is nothing different or unique that you will get. It is only that the filters now have been shifted around. In fact, basically H1 has gone to the bottom, and a good point to sort of leave this discussion and say that the shifted filter banks, we can obtain the straightforward version that you will get when you substitute these shifted versions is one which has got the IDFT form or the transpose conjugate of the DFT matrix. And so, if you were to draw it in this case, this is h naught of z, second one is h1 of z, okay. h1 of z is shifted to the right by 2 pi over m, and then this case this one is h m minus 1 of z. So, this is more of the intuitive order. Basically, you have h naught shifted to the right by this h1, h2 all the way to hm minus 1. So, this gives you the intuitive order. We can very well work with the DFT matrix as well, and we get a slightly a flipped order. Okay. Now, we move into probably the one of the most important elements of this particular unit, which is the following: spectral analysis. Very, very important. Please, if you have any questions in the material that is being presented, feel free to stop and ask. We will spend some time discussing that. We are going to take a special case, and it is a very important special case. The special case is that you have the polyphase components E naught of z, you have E1 of z polyphase component. Okay, instead of writing it as z power m, the polynomial will be E naught of z. You have E1 of z all the way to Em minus 1 of z. The special case that we are going to consider, that this is equal to E2 of z dot dot dot, all of them are equal to 1. That means they are all scalars, they are not polynomials, they are just equal to a constant. Okay. Now, very important for us to analyze what is going on. So, I would like to once again go back to the filter that we derived and see if I can just use this to simplify my drawing. Maybe it would have been easier for me to redraw the whole thing. Let me just see if we can reuse this one. Okay. So, I am going to erase those unwanted lines, keep only the ones that are necessary. And basically we have said all of these are constants, so these are gone, it is only a straight line that is connecting them. Okay. So, just erase this, we will redraw these lines. Is it okay? This is a special case that we have chosen to study, and let us just so that we are clear, this is delay number 1, this is delay number 1, this is delay number m minus 1, it is a m channel case. So, because of the structure, if this is x of n, this will be x of n minus 1, this will be x of n minus m minus 1, m units of delay. I am going to give them some new labels just for convenience of working with these signals. Let us call this as S naught of n, that is the top branch, second branch is S1 of n, they are just delayed versions, but just for convenience we are writing them in this fashion, S of m minus 1 of n. Okay, and you have the IDFT matrix and you have the outputs. Now, if you notice that what we are computing is like the inverse DFT, but I do not want to call it the inverse DFT because then we start getting confused between time and frequency domains. It is a transformation of this S vector into another vector, orthogonal transformation, and let us call these outputs as x0, x1, x of m minus 1, okay. And we are also going to give it a time index, okay. That is why I do not want to call it as think of it as frequency and time. At time n, what is your input? S naught of n at the topmost branch, S1 of n at the next branch, Sm minus 1. I am going to take apply the IDFT or the transpose conjugate of the DFT matrix, and this is x1 of n, this index is just time index n, okay. Is my notation clear? I have got these vectors, these signals S naught, S1, Sm minus 1. If I take a particular snapshot in time, I get a column vector. To that I apply the transpose conjugate matrix and I get another column vector. I call that as x0, x1, xm minus 1. Everyone's clear with this notation? Because I am going to work with this notation, you will find in a moment that is actually very helpful. So, do not forget the arrows are signals going in, m signals going in, m signals coming out. Okay. Now, this is a linear transformation, S naught of n going towards x, S naught of n going towards x naught of n. So, I am going to take the Z transform and represent this equation in the Z transform. So, this particular structure taking the Z transform, then I get xk of z, any one of these branches. If I were to write down the Z transform of that would be summation, please pay attention, I mean follow this, if there is any doubt please let me know, okay. So, before that maybe I will write down the time domain equation. Xk of n can be written as summation I equal to 0 to m minus 1 Si of n times Wm minus Ki. I will give you a moment to just sort of make sure that we have written down the equation correctly, the expression for these outputs, they are in terms of the inputs times that corresponding row of the W dagger matrix. Okay. Basically the input vector, if you were to visualize it, maybe I will just write it and then erase. The input vector is S naught of n, S naught of n, S1 of n dot Sm minus 1 of n, that is the input vector. You are processing it through the W dagger matrix. So, and this produces x naught of n, x1 of n, xm minus 1 of n, and what we have captured here is this equation. One special case, you have taken a particular row of the W dagger matrix and that is what you get. Okay. Now, taking the Z transform of this, okay, these W's are constant, so they do not affect your, so xk of Z, just rewrite it neatly, xk of Z is equal to, can you help me, I is equal to 0 to m minus 1, it will be Si of z times Wm minus Ki is what I have done, correct. Basically xk is a linear combination of some signals. If you want to take the z transform of xk, you have to take the z transforms of all the component signals, and that's it's a correct statement, a correct equation. Now what is Si of z? Si of z is nothing but z power minus I times x of z. So if you now substitute back into this equation, then it becomes I equal to 0 to m minus 1, z power minus I x of z times W m minus Ki, W m minus Ki. Okay. So the output relationship can be written in this form: xk of z is equal to x of z is common, it does not depend on I, it comes outside the summation. You get summation I equal to 0 to m minus 1 z W m k raised to the power minus I. This is a very, very key equation. So if this is the input output relationship, then this becomes the expression for hk of z, the transfer function. And now this is the point at which all the insights start to flow. Okay. So what is h naught of z? We said all the polyphase components were set to 1. So which means this is equal to 1 plus z inverse plus z minus 2 dot 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 plus z power minus m minus 1. Am I right? This is now first let us look at what does this filter look like. This is a rectangular window, we have studied this many times, dot dot dot. So if this is 0 dB, magnitude of h naught E of j omega, the first 0 will happen at 2 pi over n, the second 0 will happen 2 pi over m, I am sorry, 2 pi over m, second 0 will happen at 4 pi over m, 6 pi over m, basically multiples of 2 pi over m, dot dot dot. Another important element is that the first side lobe is at minus 13 dB. I am sure you would have verified this in the course of your filter design. Basically if you think of this as a low pass filter, it has the behavior of a low pass filter because it allows the low frequency components and suppresses the high frequency components, but it is not a very good low pass filter because the attenuation of the unwanted components with respect to the signals that are passed through is not very significant. You would typically you would like to have 40 dB or 60 dB difference between the signals that are passed and the signals that are retained or stopped. In this case it is only 13 dB, but does not matter. This is the rectangular filter. So this is what h naught of z is. Now if you go back and look at our expression, what is h of 1? It will be h of zwk. So h1 of z will be h naught of zw. If you go back and substitute, you can verify that the expressions are consistent, and in the general case hk of z is h naught of zwk. Okay. And so if you were to now sketch these filters, unlike the ideal filters that we had, let us see if we can quickly sketch them. This is h naught, h naught, the first h1, let me sketch it in red, it will be a shifted version of it. Okay. and likewise H2, yet another shifted version. The books give nice figures, so I am sure you can augment what we have drawn here with some good figures. So, basically you see that you get a filter. These are the DFT shifted filter banks, but it turns out that your basic filter was of this form, a rectangular window. So, the subsequent shifted versions also came up in this fashion. Everyone clear with what we have done so far? So, H of m minus 1, the last filter, I request you to sketch that. So, this will be 2 pi. At 2 pi you will get back the H naught. So, that is present there. H of m minus 1 will be a filter that is just shifted with respect to, so this is H of m minus 1 of z, these are all shifted versions. So, basically we spanned from 0 to 2 pi with this version. So, we can write the following statement: x naught of n, if you were asked to give a description of this, you would say that this is the output that you would get if x of n is filtered through a filter H naught of z. Output if x of n filtered by H naught of z, that is a filter and you pass it through, and that is the output that you will get. Similarly, you will all the way to x m minus 1 of n corresponds to the output if x of n filtered by H m minus 1 of z, which is the rectangular window shifted all the way to the last one. The center frequency for this will be 2 pi over m into m minus 1. This is the center frequency for the last filter, and in the general case the center frequency will be 2 pi over m into k. Okay, that will be the center frequency, and you span all the way from here to. Okay. Now, here is where we quickly start to apply the concepts that we have developed, and let us see if we can. Everyone comfortable with this figure, what we have done? The structure, the input coming through a delay chain passing through the transpose conjugate of the DFT matrix gives me a systematic set of outputs, where the first output corresponds to filtered by a rectangular window. It is rectangular in the time domain, in the frequency domain it will be a sinc function, and then these are all shifted versions of the sinc function.